In this video, our topic will be subsets and set operations. Our learning objectives will be to define the complement of a set, find all subsets of a set, how to use subset notation, find the number of subsets for a set, and then we'll look at how to find intersections, unions, and differences of sets. So let's dive in. So let's define a term here, the universal set. The universal set for a given situation, which is symbolized by a capital U, is the set of all objects that are reasonable to consider in that situation. Once we define a universal set in a given setting, we are restricted to considering only elements from that set for that particular problem. So, if the universal set is the natural numbers from 1 to 8, then the only elements we can use to define other sets in this setting would be the natural numbers or the integers from 1 to 8. A very useful tool or a clever method for visualizing sets and their relationships is called a Venn diagram. It's named because it was developed by a man named John Venn in the 1800s. We'll be looking at Venn diagrams quite a bit over the next few sections, but we'll introduce the idea here. Figure 2.1 here shows an example of a Venn diagram. You can get a lot of information from this fairly simple diagram. A set called A is being defined here. The universal set from which the elements of A can be chosen is the integers from 1 to 8. And then the set A includes the numbers 2, 4, 6, and 8. And then the elements not in A are 1, 3, 5, and 7. We will call the elements in U that are not in A the complement of A and denote it by A with a prime symbol. Call that A prime, or the A complement. Okay? So in the Venn diagram here, the rectangle represents the universal set. And you'll notice that inside the rectangle, we have all the integers from 1 to 8. Since this is the universal set, that we're saying that any other sets are only allowed to contain these values. Set A contains some of these values, but not all of them. It contains the values 2, 4, 6, and 8. And notice how the circle here represents set A. And that circle is completely inside the rectangle, right? To indicate that the set A is a set that does contain some of the values from the universal set, right? So the numbers written inside the circle are the values that are part of set A. The numbers outside the circle are the numbers that are not in set A. Those represent the complement of A. So we'll say the complement of set A, symbolized A prime, is the set of elements in the universal set that are not in A. Using set builder notation, the complement of A is A prime. And we could say that A prime is equal to all x, the vertical line means such that, so all x such that x is an element or a member of the universal set, and x is not a member or element of set A. Right? In a Venn diagram, the complement of a set A is all the things inside the rectangle that are not inside the circle representing set A. Right? So figure 2.2 is a simplified version, right? So the rectangle is the universal set. The circle is set A. The region inside the rectangle but outside the circle, that's the complement of A. Let's look at some examples. Example 1 here. Find the complement of a set. So let's let the universal set be the letters VW, X, Y, and Z. Set A is the set W, Y, and Z. Let's find A prime, the complement of A, and draw a Venn diagram that illustrates these sets. And then we got a second question: what is the complement of the universal set for a given situation? So let's start with the first question. Using the list of elements in U, we have to basically eliminate the ones that are also in A, right? So let's just write down the universal set here. That is V, W, X, Y, and Z. And we know that set A, which is written up here, includes the letters W, Y, and Z. So the complement of A would be all of the letters in the universal set except for these ones, right? So what we could do is in our universal set, I could just literally cross out the ones that are in A. So the W, the Y, and the Z. And what's left is a V and an X, right? So we could say that A complement is equal to V comma X. The Venn diagram is sketched down here. Okay, here's the Venn diagram. The rectangle is the universal set. You'll notice that inside the rectangle are all the letters V, W, X, Y, and Z. The circle represents set A. Inside the circle, we find the letters W, Y, and Z. The region inside the rectangle but outside the circle is the complement of A. That region has the letters V and X. Okay, how about this second question here? What is the complement of the universal set for a given situation? Well, there are no elements in a universal set that are not in the universal set, right? So according to the definition of a complement, there are no elements in the complement of a universal set. So that means the complement of the universal set is the empty set. Okay, so this is part A here. Part B. We'll just write the symbol for the empty set here. Okay. There are no elements in a universal set that are not in the universal set, right? The universal set contains all of the possible elements for a given problem. So the complement of the universal set is the empty set. Okay, let's talk a little bit about subsets. If every element of a set A is also an element of set B, then we say that A is called a subset of B. Okay, so like if we look at the Venn diagram in figure 2.3, we could say that set A is a subset of the universal set, right? Because every element in set A is also an element of the universal set. So there's an example. The symbol, sorry, let's fill this in. So blank here is a subset. Okay, if every element of set A is also an element of a set B, then A is called a subset of B. This symbol right here is used to designate a subset, right? So in this case, we could write this notation here, which we would literally read as A is a subset of B. So a few notes about subsets. Every set is a subset of itself because every element of a set A is obviously an element of set A, right? So this is a true statement. A is a subset of A, right? Because it meets the definition of what a subset is. It's also true that the empty set is considered a subset of every set. The empty set has no elements, right? So we could say for any set A, you cannot find an element of the empty set that is not also in set A, right? So for this reason, the empty set is considered a subset of every set. Okay, let's look at an example of subsets here. If we start with the set containing the letters X, Y, and Z, let's look at how many subsets we can form. So let's break this down by subsets by number of elements, right? So let's look at the subsets of this set that contain 3 elements. Well, there's only one, and that's the set itself, right? The set X, Y, Z. So there is one subset that contains 3 elements. How about 2 elements? Okay, there are 3 subsets of the set X, Y, Z that have 2 elements. The set XY, XZ, and YZ. And then there are 3 subsets of the original set that have just 1 element. The subset containing only X, the subset containing only Y, and the subset containing only Z. And then we always have to list the empty set as well, because the empty set is a subset of every set. So there is one subset that contains 0 elements, the empty set, right? So that's a total of 1 plus 3 is 4, plus 3 is 7, plus 1. Looks like 8 subsets. There's 8 possible subsets of a set that has 3 elements. Okay. So for a set with 3 elements, we can form 8 subsets. Let's look at another example. Find all subsets of set A, which contains the words cold and flu. We'll list them down here. Well, the set itself is always a subset, so we can list that. Cold, flu. And then 2 other subsets are just ones containing each individual element. So the set containing only cold, and then only flu. And then, of course, we have to consider the empty set as well, because that's always a subset of any set, okay? So we see that there are 4 subsets, right? So we can say a set with 2 elements has 4 subsets. Okay. Okay, some more notation here. To indicate that a set is not a subset of another set, we use this symbol. This is the subset symbol with a slash through it, right? So that means not a subset. And then if set A is a subset of set B and is not equal to B, then we call A proper subset. Okay, a proper subset of B. And the symbol for a proper subset is this symbol. It's the same symbol, but without the horizontal line at the bottom. Okay. And we would interpret that as A is a subset of B, and also A is not equal to B, right? If we If we back up a little bit and consider these two examples, right, in this case here, we started with the set X, Y, and Z, and we listed all the subsets here. This first set right here is not a proper subset, right, because it's equal to the original set. All of the other subsets are considered proper subsets because they are subsets that are not equal to the original set. If we come down to example 2 here, this subset, the first one we listed, is not a proper subset because it's equal to set A. All the other subsets are proper subsets. So when we consider all the possible subsets of any set, all of the subsets will be proper subsets except for one, which is the one that is equal, right, to the original set. Let's consider a Venn diagram that illustrates a proper subset in figure 2.4 here. So the blue, the inner circle, is entirely inside the red outer one. And there's an element inside the red circle that is not in the blue one. So if we look at this Venn diagram, what it's illustrating are these three sets. The universal set includes all the numbers inside the rectangle. And that would be the counting numbers 1, 2, 3, 4, 5. Set A includes all of the numbers inside the red circle. That would be 1, 3, and 5. And then set B would be all of the numbers inside the blue circle. That would be the numbers 1 and 3. Notice that all of the numbers in set B are also in set A, right? Both B and A contain the elements 1 and 3, but set A contains one additional element, set 5, so A and B are not equal to each other, so that means B is a proper subset of A. Okay, so let's do another example. We want to find all of the proper subsets of the set that contains the words marketing, English, psychology. Let's list them down here. So remember, the proper subsets are the ones that are not equal to the original set. So we're not going to include the subset that has all the same elements. We'll only include subsets that have fewer than 3 elements. Okay, so one possibility here is one that contains the words marketing, comma, English. Marketing, comma, psychology. We've got English, comma, psychology. Then we have 3 subsets that contain only one element. The subset that contains only marketing. Oopsies, that should be a brace, not a parentheses. Let's see if I can fix that. And then we've got the subset that contains only English. And the subset that contains only psychology. And then also we have to consider the empty set, because that's also a subset. Okay. So it looks like we have 1, 2, 3, 4, 5, 6, 7 proper subsets. This symbol here is used to indicate that the set is not a proper subset, right? So it's the proper subset symbol with a slash through it. Okay, let's just do another example just to help us understand all of this notation that we've been introducing. And we want to decide if each statement is true or false. Okay. So let's start with A. So what do we have here? We have the set 1, 3, 5. This is the symbol that means subset. So it's saying 1, 3, 5 is a subset of the set 1, 3, 5, 7. So we have to ask, are all the elements in this set also in this set? It looks like they are, right? This set contains 1, 3, 5. This set also contains 1, 3, 5, right? So all of the elements in this set are also in this set, so it is a subset, right? This set is a subset of that set. So the statement is true. Okay. Coming down to B. Is the set AB this is the symbol for proper subset. Okay. Is the set AB a proper subset of AB? Okay. Well, even though AB, this set, is a subset of this set, it's not a proper subset. It's not a proper subset because the two sets are equal. Okay, they're subsets, but they are not proper subsets. So this statement is false. Okay. Let's see. Let's come down to C. So this is saying this first set is in set builder notation. And it says all x, sorry, where are we? Okay. All x such that x is an element of E, so E would be the even natural numbers. And x is greater than 10. Okay. So this set here would be the set of even natural numbers greater than 10. And we're asked, and this is a set for proper subset, and then n represents the set of all natural numbers, right? So are the set of even natural numbers greater than 10 a proper subset of the set of natural numbers? Okay. Well, certainly every element in the first set is a natural number, but not all natural numbers are in this set, right? So yes, this set is a proper subset of this set because all the elements in this set are also in this set, and these two sets are not equal to each other. So for C, yes, this is a true statement. All right. Let's come down to D. What do we have here? This is saying the set RST is not a proper subset of the set TSR. Okay, well, these two sets are actually identical. I mean, the elements are listed in a different order, but that doesn't matter. They contain the same elements, so these two sets are equal to each other. So this set is a subset of this set, but it's not a proper subset, right? So it's correct to say they're not proper subsets. So the statement here is true. Okay. Okay. E, what do we have here? This set is the set that contains Lake Erie, Lake Huron, and then we're saying is not a proper subset of the set of Great Lakes. Well, Lake Erie and Lake Huron are two of the Great Lakes. Two of some of the Great Lakes, right? This does not include all of them. So yeah, this is a proper subset of the set of all Great Lakes, right? So it would be incorrect to say that it's not a proper subset. So this statement is false. Oops. Sorry. False. All right. F, what do we have here? The null set is a proper subset of the set containing the elements 5, 10, and 15. And that's true. The because the empty set is considered a proper subset of every set except itself. Okay, so for F, this is true. All right. G, we have the set UVWX. This is saying subset, right? So we're saying this set is a subset of the set containing X, W, and U. This is false because the element V is an element of this set, but not an element of this set, right? If we reversed it, if we put this set over here and this set over here, that would be a true statement, but the way it's arranged this way, it's not a true statement, okay? This set is not a subset of this set. So this would be false. Okay. And then finally for H, this is saying the set containing the number 0 is a subset of the empty set. Well, this set here, the set on the left has one element, 0. The empty set has no elements, so this statement is false. Okay, a general rule for finding the number of subsets for a finite set, a set that has a finite number of elements. If a finite set has n elements, then the set has 2 raised to the power of n subsets and 2 raised to the power of n minus 1 proper subsets. Okay. So just to use this example here, find the number of subsets and proper subsets of the set containing the elements ace, king, queen, jack, 10, 9. So that is 1, 2, 3, 4, 5, 6 elements. Okay, so let's answer question A here. The set has n equals 6 elements. So there are 2 raised to the power of n, or 2 raised to the power of 6, which equals 64 possible subsets. And for any set, there's always only one set that's a proper, that's not a proper subset, right? The set that's equal to the original set. So there would be 2 to the n minus 1, or 63 proper subsets. So this rule only gives you the number of sets. It does not tell you what those sets are, right? It would be a challenge to list out all 64 of them. But it's a fairly simple to figure out the total number of subsets. Okay, so part B, explain why the number of proper subsets for a set is always 1 less than the total number of subsets. Well, when finding proper subsets, there's only one subset excluded from the list of all subsets, the original set itself, right? So there will always be one fewer proper subsets than the total number of subsets, right? The only subset that's not a proper subset is the set itself. Okay, let's introduce some new concepts. The intersection of two sets, A and B, which is symbolized using this symbol here. Looks like kind of like an upside down U. We say A intersection B. This is the set of all elements that are in both sets. So in set builder notation, we could say that A intersection B, this is equal to all X such that X is an element of A, and also X is an element of B. For example, if set A contains the numbers 10, 12, 14, 15, and set B contains the numbers 13, 14, 15, 16, 17, then we can see that these two sets contain two elements that are shared in common. 14 and 15 are in both sets. So the intersection of A and B would be the set that contains the elements 14 and 15, right? Since 14 and 15 are the only elements that are common to both sets. We can illustrate an intersection with a Venn diagram. So here we can see that, again, the rectangle represents the universal set. The circles, this circle represents set A, the red circle, then the blue circle represents set B. And we see there's a little bit of overlap between the two circles, right? The overlap region, that represents the intersection. And inside that overlap region, we put the numbers 14 and 15, right? Because those are the numbers shared in common. Over here, we have the numbers 10 and 12. This region is inside the circle for A, but outside the circle for B, right? So this contains the elements in set A that are not in set B. So those would be 10 and 12. Over here, in this region, we have the elements in set B that are not in set A. And those would be 13, 16, and 17. Okay. Intersection is an example of what we call a set operation. This is a rule for combining two or more sets to form a new set. The intersection of three or more sets consists of the set of elements that are in every single one of the three sets. Note that the word "and" is sometimes used to indicate intersection. Okay? The intersection of A and B is the set of elements in A and also in B. Let's look at an example for finding intersections here. Three experimental medications are being evaluated for safety. Each has a list of side effects that has been reported by at least 1% of the people trying the medication. This is a blind trial, so the medications are simply labeled A, B, and C. The side effects for each are listed below, right? So we have three sets, and each set is a set of side effects. Set A, nausea, night sweats, nervousness, dry mouth, swollen feet. Set B, weight gain, nausea, nervousness, blurry vision, fever, trouble sleeping. Set C, dry mouth, nausea, blurry vision, fever, weight loss, eczema. Okay. Find each requested set. Let's start with A. So A, we are trying to find the intersection of set A and set B. Okay. Okay, so for this, maybe we'll just actually circle these. We have to find the elements that are in A and also in B, right? Maybe we'll just start over here with A. We'll start with nausea. So we see that nausea is in A. Let's check. Is it also in B? Yes, it is. It's in A. It's also in B, right? I can maybe just circle those. Nausea is in A and B. What about the other ones? Night sweats. That's in A. Is it down here in B? Nope. Nervousness. It's in A. Do I find it in B? Yep, there it is, nervousness, right? So nervousness appears in both. Okay. Dry mouth, that's in A. Is it in B? Nope. Swollen feet, that's in A. Is it in B? Nope. Okay, so the intersection of A and B contains only two elements. The elements nausea, common nervousness. Okay, let's go ahead and erase these since we're moving on. Let's see. For B, we're trying to find the intersection of set B with set C. So we can do a similar sort of analysis here. Let's just start by going through the elements in B and seeing if they also show up in C. So weight loss, that shows up in B. Is it also in C? Yep, there it is, weight loss, right? Shows up in both. Weight loss, oh, shoot, I can't read today, can I? This one is obviously weight gain, and this one is weight loss, sorry. Weight gain shows up in set B, and weight loss shows up in set C. Weight gain does not show up in both of them. So sorry for that confusion. Okay, let's move on to nausea. Nausea shows up in set B. Nausea also shows up in set C. So those ones are shared in common. Okay. Nausea. Okay. Nervousness, that shows up in set B. I don't see it down here in C. Okay. Blurry vision, that shows up in B. It also shows up in C. So there's another one that's shared in common. Blurry vision. Okay. Fever, that shows up in B. It also shows up in C. Okay. Fever. Okay. Trouble sleeping shows up in B, but not in C. So it looks like those are the only three elements shared in common. So the intersection of B and C contains nausea, blurry vision, and fever. All right, let's erase these. Come down here to C. For this last one, we're trying to find the intersection of all three sets. A, intersection B, intersection C. Okay. Which elements are shared in common between all three, right? So we can probably actually kind of use the results of the first two, right? Because we can see that nausea and nervousness are shared in common between A and B. Nausea, blurry vision, fever are shared in common between B and C. So it's not too hard to see that the only thing shared in common between all three of them is nausea, right? Nausea is shared between A, B, and C. And you can do another careful check if you want to, but you'll see that the only element shared in common between all three sets is nausea. Okay. When the intersection of two sets is the empty set, the sets are said to be disjoint. Okay, here's a Venn diagram illustrating disjoint sets. Again, the rectangle is the universal set. A and B are sets within the universal set, and the circles for A and B do not overlap at all. So they share nothing in common. So they are disjoint. Okay. Another term to define here, the union of two sets A and B, symbolized by this symbol, looks like just a U. We say A union B. This is the set of all elements that are in either set or B or both. In set builder notation, we would say A union B would be the set of all X such that X is an element of A or X is an element of B. For example, if set A contains the numbers 5, 10, 15, 20, and set B contains 5, 20, 30, 45, then the union would be all the elements in A combined with the elements in B. Okay. So that would be 5, 10, 15, 20, 30, 45. Okay. Notice that the elements 5 and 20 are in both sets, but when we combine them into a union, we only list them once in the union. The Venn diagram is shown here, right? So basically the shaded pink is the union, right? So the union contains the intersection, but it also contains all the elements in A that are not in B, and it contains the elements in B that are not in A, right? Anything in A or B or both. Okay. All of the elements in either set. All right. Let's look at this example here. Finding unions. So these are the same sets from the previous example, right? The side effects. For each of the following, describe verbally what each set represents. Okay. So again, to find a union, we just make a list of all the elements from each set without writing repeats. Right. So A union B, this is the set of side effects that were reported by more than 1% of subjects taking either medication A or B. Right. So if we were to write this out, A union B, I might just start with set A. I would have to include nausea and night sweats and nervousness. And dry mouth and swollen feet and then coming down to set B, I would clearly also have to include weight gain and then we have nausea, but I've already listed nausea, right? So I don't need to list it again. And then we have nervousness, but I've also already listed nervousness. I don't need to list that again. So then we come over here to blurry vision. Okay. Fever. And trouble sleeping. Okay. That's the union of A and B. Okay. A union C. A union C. All the elements in either A or C or both, right? So this would include nausea, night sweats, nervousness, dry mouth, swollen feet, right? Let's see. In set A, the first one there is dry mouth. We've already listed that. We've also already listed nausea, so we got to include blurry vision. Okay. Fever. Okay. Weight loss. And eczema. Okay. A union B union C. Right. A union B union C. This is just a comprehensive list of all the side effects, right, caused by all three of the medications. Nausea, night sweats, nervousness, dry mouth, swollen feet, weight gain, blurry vision. There's a lot of them. Fever, trouble sleeping, weight loss, eczema. Right, that's a list of all the side effects. Okay, when we are performing set operations involving more than two sets and more than one operation, we use parentheses to indicate an order of operations. So to illustrate that here with example 8, using the same sets from the previous two examples, find each requested set and write a verbal description of what each set represents. Okay. So here we have A union B intersection C. Okay. So this is saying for part A, it's basically saying first find A union B, and then take that and intersect it with C. Okay. So let's see, we've got A union B intersection C, right? This is where it might be helpful to kind of back up. So A union B we found right here, right? And we want to basically figure out which elements are shared in common between this set and set C, right? And those would be dry mouth, right? They appear in both. Nausea appear in both, right? Blurry vision appear in both, and fever appear in both. Okay. Fever, yeah. So those are the ones that are shared in common. Okay. But the key here is that you find the intersection first, and then you find those elements that are shared in common between you find the union first, A union B, and then you figure out which elements are shared in common between this set and this set, right? The intersection second. So this would be dry mouth, nausea, blurry vision, and fever. Okay. The next one we have A intersection B union C. Okay. So this is saying take the union of B and C first, right? And then find the intersection of that with A. Okay. So B union C, I guess we didn't actually find that here, but that's basically everything, right, that is shared in common between, so basically everything that's in B or in C, right? So we would figure that out, and then we figured out, well, what if we combine these two sets together into a union, and then what values are shared in common between that and set A, right? And that would be nausea, dry mouth, and nervousness is what you would find if you did that. Okay. Nausea, dry mouth, and nervousness. All right. Let's see, this last one, A intersection B union C. Right, so A intersection B union C. So because the intersection is in parentheses, it's saying we find that first, and then we find the union of that with set C, right? A intersection B, I believe we found that up here, didn't we? Yeah. A intersection B is nausea, nervousness. And if we take the union of that with C, right, then we have to include nausea and nervousness along with any other elements that are also in C, right? So that would include dry mouth, blurry vision, fever, weight loss, eczema. Okay. So let's write that down here. Okay. So nausea, nervousness, dry mouth, blurry vision, fever, weight loss, eczema. Okay, hopefully that helps us to illustrate how to do some set operations. Okay. Caution. When combining union and intersection with complements, as we will see in the next example, we'll have to be extra careful. Okay. We want to pay particular attention to the parentheses and to whether the complement symbol is inside or outside the parentheses. Okay. So in example 9 here, going back to our sets of side effects, recall that these were reported by at least 1% of users. The universal set below is the set of all side effects reported by any users. Use this to find the following sets. Okay, so there's the universal set. So we want to find A complement, intersection, C complement. Okay. So for each of these, right, for A, first we have to find A complement. Okay. And for this, you might need to kind of review what sets A, B, and C are. But A complement, right, will be any elements that are in U but are not in A, right? So A includes nausea, night sweats, nervousness, dry mouth, swollen feet, right? So A complement, right, would be the elements that are in U but not in A, right? So this would include weight gain, okay, blurry vision, fever, trouble sleeping, weight loss, right? Eczema, motor mouth, okay, darting eyes, uncontrollable falling down, okay. We'll just do the first one here, and then I'll kind of leave the other ones for you to work on your own, because it's good practice. C prime here is everything that's in set in U but not in C, right? So you can look at C up above and then compare it to U to figure this out, right? But it includes night sweats, nervousness, swollen feet, weight gain, trouble sleeping, motor mouth, darting eyes, okay, uncontrollable falling down. Okay, so you got to find the complements first, and then this is asking for an intersection, right? So it's asking for what is shared in common between these two sets that we just found here. Okay. A complement, intersection C complement. Okay. So what do they share in common? Well, they both have weight gain. Okay, maybe we can just circle them. Right, weight gain. They both have trouble sleeping. Okay. They both have motor mouth. There. Okay. They both have darting eyes. There and there. Right. They both have uncontrollable falling down. There and there. Okay. So this would be, weight gain, trouble sleeping, motor mouth, darting eyes, uncontrollable falling down. Okay. So I'll leave these ones for you to work on, but for this one, keep in mind that what you have to do is you have to find the intersection of A and B, right? Then you find the complement only after you find the intersection, right? And then we take that result and intersect it with C. Over here, we have to find the complement of B and the complement of C separately, and then perform these other operations. Okay. I want to come down here. We're almost done with this video. It's getting kind of long. Just the last topic I want to go over here is set subtraction. The difference of set A and set B is the set of elements in set A that are not in set B. In set builder notation, we could say that A minus B is equal to all x, such that x is an element of A and x is not an element of B. Okay. Right, so if we're kind of considering the same sets from the previous examples, again, let's just do A minus B, right? This would be the elements. Basically, we'd start with set A, and we would remove the elements that are in set B, right? So the elements in set A that are not in set B, okay? And you can go compare those sets from what we wrote from the earlier examples. But if you do that, you'll see that the sets that are in A but not in B would be night sweats, okay, dry mouth, swollen feet. Okay. So pretty straightforward idea. I'll leave these two for you to work on. The only one that's a little interesting is this one. And just remember that you always do what's inside the parentheses first, right? So A minus B, this, just the parentheses, well, we just found that right here, right? So then we subtract C, right? So we would say, what are the elements that are in this set, but not in C, right? You got to figure that out. So, okay, hopefully that was helpful, but we'll stop here for now. Thank you.